Hello again, we are in chapter 15, and here we go a little bit into image processing and maybe sort of playing around with images and things that Python can do with images. And this is something that has been done many times. You can look at around the web and different methods, different genetic evolutionary methods. We are going to do our own version of it here. So the idea is to take an image, a famous image, like in this case the face of the Mona Lisa, and try to reproduce it or create an image that is recognizable and is close to this picture by combining together polygons. In our case, we'll try it with triangles mostly. So starting with a black background and then putting a semi-transparent, colorful triangles in different colors and in sizes and locations. Can we pile a certain amount of triangles and recreate something that looks like that? So the genetic algorithm is trying to find those 100 triangles that will be the most similar, and as the fitness, it compares pixel by pixel and tries to find a certain measure of difference between the pictures. And the program we are going to use here is the Reconstruct polygon, the first one. And you can see that we are going to use here triangles, because this is the polygon size, how many sides in it. And we have the number of polygons set to 100, so we're trying to use 100 triangles to recreate the Mona Lisa. We will later, or you could later, try smaller amounts, and we will talk about it. But we're going to go for 5,000 generations, so this program is going to take a while. So for the first time in our programs, we're actually going to use here not just for demonstration purposes, but also just to make it go quicker. You will see that we are going to use multiprocessing. And here we have a number of processes, 20, but we can make it larger if we have a larger computer. And actually, I'm going on this computer. I'm going to make it 40 because I think it's a little bit faster than the original computer that it ran on, and it may be able to support more. So we shall see how long that takes, but it's probably gonna take a while in any case. What this program does also, it goes into the images directory and it saves snapshots of the progress. So at the end we can go back and look and see how the different I think every 100 generations, and there is a callback. Do you see that? You can see that there is elitism and callback. So we made a small modification to the elitism, so it has a callback every 100 generation or so, and it saves a snapshot of what we achieved at that point, so we can go back later and look at it. So let's start running it, because it's going to take a while. And as it runs, we will be able to see that in the images there will be more files appearing, but we will have to wait. We can see that the generations are running quickly, but we still have 5,000 of them. So I'll see you at the end of that. So we are back, and this program just finished running. So it ran for 5,000 generations, and it's showing us the best solution, which is the list of triangles, their location and transparency and color, which is sort of meaningless to us just to look at the numbers. So we will see a visual in a second. Let's look at what we see here. Also is a graph. Let's look here, and we can see the graph of how the maximum and the average performance was over the generations. So it looks like maybe it will even go a little bit better, but not much. It's pretty much changing very little in the last 1,000 generations. And remember that this is minimizing the distance, the difference between the picture that we want, which is the Mona Lisa, and the picture that was created with the triangles. So we have 100 triangles. So what we see on the left side is the original Mona Lisa. On the right side is the one that we compose of the triangles. And in the middle is a blurred version of that, just sort of like squinting, so it will take away a little bit of the sharp edges that we have here. And that looks pretty good, at least to me. It looks like a pretty good approximation of Mona Lisa with 100 triangles. And what we can do also is look at the images, at the snapshots that were saved every 100 generations. You can see that there is a PNG saved up to the 5000, and if we go to this folder, we can see those pictures. So if we look at the first one, it doesn't look much, but over time, if you just take something random, it looks more and more like the Mona Lisa until we get to the end one. And I have this image that's taken from the book where I put it together, and you can see after 500 generations, etc., and after the 5000, where it starts to look pretty close. Now, if I went again and did it instead of with 100 triangles, I would only use 20. We would get that, which is not amazing, but you can still see, especially if you look at the blurred version, you can still see a something that looks like maybe a picture of a woman. Maybe you can tell it's the Mona Lisa, but if we go down to 15, it's already losing that. 15 triangles don't seem to be enough. So we ran one other experiments where we, instead of comparing that picture, the triangle created picture, to the original, to decide what are the best triangles, we are going to try to compare the blurred version to the original. So the fitness is measured on the blurred version, and this is the second program here that's called Reconstruct with Blur, Polygons Blur. So here we use a blur function. We can maybe just compare these two quickly and kill this, and we can see that we have only 20, and then we can try 15. So let me go to the 15, and we can see that we have a different result. We want the results to be kept separately. And the difference between the two programs is the get difference, where here the get difference has to do, we add some blur to it. We send blur equals true, so it will blur the picture using some Python library before it measures the difference. So let's run this version. This should go perhaps a little faster, but it's still going to, let's see, the generation is still 5000, so it's going to take a while. And we'll let it run and wait for the results. Okay, so we are back, and this run has finished. And let's look at the resulting image. You can see, by the way, that in the images we have under results, we have the blur directory, which has the results of the 315, and then we have the 3100 here. So to remind you, we were running with only 15 triangles, and we were trying to improve upon this. So this was with 15 triangles when we were measuring the difference between the two pictures as what we're trying to optimize. And now we were running 15 triangles, but we changed the fitness, so it will, before comparison, it will blur the image. And what we get is, I would think, quite a bit better. You can sort of recognize that it's a face. Maybe even you can tell that it's a Mona Lisa by looking at this. A lot better than this. A lot better than what we had here. So it looks like perhaps that with a low number of triangles, there may be an advantage comparing using the blurry version for the fitness calculation. You can go now and experiment, try all kind of other combinations. Just wanted to show you one more experiment. Here we went back to the 100, but instead of triangles, we use hexagons. So we changed that number of sides, the size of the polygon, to 6. And when we use the blurred image as the source of fitness, we get something quite funky like that. So you can experiment and hopefully see some other interesting results. So this is it for chapter 15. We'll talk again in chapter 16.